go in the direction. Congratulations. So
thank you.
It's going to happy to have you. So we will learn about trace estimation and determinant. So go ahead, Alicia.
Thank you very much, and I mean, thank you very much for the invitation. So in this presentation, I will talk about randomized trace estimation and determinants, and this is part of the work I've done during my PhD with my advisor, Professor Daniel Kressner, also from EPFL. So first of all, I will try to motivate why computing the determinant of large symmetric positive definite matrices is an interesting problem, and I will explain how this is connected to estimating the trace of a matrix. So this paper here, basically I got into trace estimation because of this paper here. So here is the first, this was the first time I saw randomized trace estimation. And this paper is about Gaussian processes, which are now a big thing in data science. So I thought I would start with this one. And basically then the rest of the talk is just numerical linear algebra. So very briefly, a Gaussian process is a distribution on the space of functions with a certain mean function mu and the covariance function k. And the goal here was to train a Gaussian process on a lot of data, say 500,000 data points, which means that you're given a class of possible covariance functions k, which depend on some hyperparameters theta, and you want to find the values of theta that best fit the data. So the function that you have to minimize, the log likelihood, is something of this form. So you have two terms. One term, which is the logarithm of the determinant of a matrix K, which I will describe now, and the other term is this one. So for this talk, I'm more interested in this term here. So K here is the discretization of K of the covariance function on the Cartesian product x times x. So this is a 500,000 by 500,000 matrix, and it's huge. And it's symmetric positive definite because that K is a covariance function. So, and yeah, in this paper, they use randomized trace estimation. So in general, computing the determinant comes up a lot in statistical learning, but has also other applications, for example, in lattice quantum chromodynamics, Markov random field models, or graph theory. And well, if you have to compute the determinant of a symmetric positive definite matrix P, well, for sure, you cannot use Laplace expansion. This is just a bad idea because it takes exponential time. One thing you can do is go via eigenvalues. So the determinant of a matrix is just the product of its eigenvalues. So you can compute the eigenvalues and take the product. Or the standard method is actually to use a Cholesky factorization of the matrix B. So this is what MATLAB does, I believe. And so basically, if you take a Cholesky factorization of B, so a decomposition of the form L transpose for a lower triangular matrix L, then the determinant of B is the product of the determinants of L and transpose, which are the same. So, and the determinant of a lower triangular matrix is just the product of its diagonal entries. Now, the problem is that if you don't, unless L is sparse and nice, computing a Cholesky factorization costs cubic time, so you cannot do that for really big matrices. So the algorithm I'm talking about, this technique of randomized trace estimation addresses the problem in a different way, like sort of in a cheaper way, but only gives you an approximation of the determinant. So for the application I mentioned before, they were happy with an estimate of the determinant with, say, 1 or 2 digits of accuracy. So now let me get to the connection of computing the determinant with computing the trace of a matrix. So for this, we need the definition of matrix function. I wrote it here. So you can define it for any matrix, but for this talk, I only need it for symmetric matrices. So if you have a symmetric matrix B, you can take a spectral decomposition of B. So the composition of the form Q times diagonal matrix containing the eigenvalues times Q transpose. And if you have a real valued function f, which is well defined on the eigenvalues of B, you can define the matrix function f of B to be this product of matrices. So just evaluate f in the eigenvalues and you multiply by Q and Q transpose. So the function I'm going to talk about is the logarithm, but you can do, like, for example, the inverse or the exponential of a matrix can be defined in this way as well. So the result that allows to connect the computation of the determinant with the trace is this one, which states that if you have a symmetric positive definite matrix B, then the logarithm of the determinant of B is the trace of the matrix logarithm of B. And this is easy to see because so the logarithm of B would be this one with log instead of f. So its trace would be the logarithm of lambda 1 plus the logarithm of lambda 2 and so on. And the left-hand side here, so the determinant is the product of the eigenvalues. So if you take the logarithm of a product, you're just getting the sum of the logarithms of the eigenvalues. Note that, okay, so this may seem unnecessarily complicated at this point because in general, computing a matrix function like this one still has cubic cost in the size of the matrix. But the trick is this randomized trace estimation algorithm will not need to compute the whole matrix logarithm of B. So before going on, I would like to mention that trace estimation has there are other quantities that can be expressed as the trace of something, of suitable matrices. For example, probably the simplest example is the Frobenius norm of a matrix, which is, I mean, the square of the Frobenius norm is the trace of B transpose B. And I mean, you can use randomized trace estimation also to estimate the Frobenius norm of a matrix. And then also other Schatten P norms and the trace of other matrix functions. For example, the trace of the inverse, the trace of the cube of a matrix, or the trace of the exponential of a matrix. Okay, so the Hutchinson trace estimator. Okay, so the objective now is to estimate the trace of A, where A is a symmetric, possibly indefinite matrix A of matrix of size n by n. And we assume that A is available through matrix vector multiplications. So somehow we don't know the entries of A, but we can do matrix vector products with A. So this setting makes sense. So at the end, for the determinant, what we want is to estimate the trace of the logarithm of B. So it sort of makes sense that we assume that matrix vector products with the logarithm of B are available, because there are because computing a matrix like f of B times a vector can be done faster than computing the whole f of B if you use Krylov subspace projection method, basically. So this is something I will tell you about later. So this is more or less the outline of the rest of the talk. So the main part of the talk is about this randomized trace estimator algorithm, which is the Hutchinson trace estimator, which will be introduced in the next slide, and its convergence analysis. And I will show a couple of numerical experiments. And this is done for a general matrix A. So this is not the approximation of the determinant yet. Then I will tell you how to compute. Okay, I wrote quadratic forms. So basically, okay, so basically what this Hutchinson trace estimator uses is not really these products, but quadratic forms involving f of B times B. So I will tell you how to compute that using, yeah, I will tell you. And then I will combine the first two parts the first two parts to get a result for log determinant estimation. Okay, so let's get started with the Hutchinson trace estimator. I recall that A is an n by n matrix, symmetric, indefinite, and we can do matrix exact. I assume everything is exact for now. Exact matrix vector products with A. So the basic fact that we need is that for a random vector X of length n, such that the expected value of XX transpose is the identity, we have that the expected value of X transpose AX is the trace of the matrix A. And so I didn't include the proof here, but it's actually one line because you write down this quadratic form as the sum of xi, xj, aij, and then by the linearity of the expectation, like the expected value of xi, xj is 1 only if I is equal to j. So what you get is exactly the trace of A. So the assumption on the random vector X is very general. So you could use like any vector that satisfies this, but in practice, the most common choices are standard Gaussian random vectors. So with entries distributed like this, and I will just call them Gaussian vectors. I mean, when I say Gaussian vectors, I mean the standard ones, or Rademacher random vectors which have IID entries which are plus or minus 1 with equal probability. So just a note here. So here is the variances of this random variable here. By diag of A, I mean the diagonal matrix containing the diagonal entries of A. So this in particular means that if you have a diagonal matrix A and you compute X transpose AX, for a Rademacher vector, you obtain exactly the trace of A. While for Gaussian vectors, this is not the case. But anyway, okay. So this result, so the idea of the Hutchinson trace estimator is that you take capital N, you take a bunch of independent copies of this random vector. Then you compute the corresponding quadratic forms, and you average them. So just to fix the notation, I'll call capital N the number of samples, and denote by trace capital N of A this estimate here, just to say that okay. So we use this notation. So this is an example to show you how more or less how this estimator behaves. So here I took a matrix A, which is symmetric. It doesn't really matter what matrix it was, but it was random. And then I've plotted for each number of samples from 1 to 1 million. I computed this estimate here, and I'm plotting the absolute value of the absolute error here, the approximation. So you see it's a like super wiggly line because it's I mean there's randomness in it, but overall it converges as 1 over square root of n, 1 over square root of the number of samples, which is what we would expect for a Monte Carlo algorithm. So now in the rest of this first part, I would like to tell you a bit more about this big O thing. So like give you more precise convergence results for this Hutchinson trace estimator. So we focused on indefinite matrices. And this is because, okay, so let's say for symmetric positive definite matrices, there's more literature on this problem. But for the case in which A is the logarithm of a symmetric positive definite, we need bounds for indefinite matrices. So basically, even if B is a symmetric positive definite matrix, the logarithm of B may be indefinite. So the bound, so basically the only bound that was in the literature about general bound for indefinite matrices is this one, and says basically it's a bound on the number of samples, capital N, that ensure that you get an approximation to the trace with accuracy epsilon, with failure probability at most delta. So this result is for both Rademacher vectors and Gaussian vectors, and it contains, so both of them contain a factor 1 over epsilon square, which gives you this 1 over square root of n convergence that we've seen, and that's nothing you can do about that. Then they contain a logarithmic dependence on 1 over delta, which is okay. This one also contains a factor log n, but we shouldn't worry too much about that. And then they both contain the square of the nuclear norm of the matrix A. And what I'll show you in the following is basically you can replace this nuclear norm square with the Frobenius norm square, which can be smaller by a factor n. Okay. So one thing I should mention is you could also rescale this matrix. For this case, you can also rescale the matrix in such a way that it becomes symmetric positive definite, and then use the bounds for symmetric positive definite matrices. But it doesn't necessarily like work. Like you obtain an explicit dependence on the size of the matrix, which is something we try to avoid. So first of all, I claim that it's sufficient to look at only one quadratic, at bounds for only one quadratic form, because you can write the Hutchinson trace estimator, so this thing, as one quadratic form, like one corresponding to a big matrix, a big block diagonal matrix containing rescaled copies of A on the diagonal, and a vector, like a long vector obtained by stacking to one after another all the x1 until x capital N. So we only need tail bounds. So let's say once we have tail bounds of this form, so of this form for one quadratic form, then automatically we can get tail bounds for the Hutchinson trace estimator. So this is what happens for Gaussian vectors. So basically, one can prove that you get accuracy epsilon with this failure probability. And the failure probability, so the big term, the important term here is basically this 4 times the squared Frobenius norm of A. And to get this, you can use more or less standard techniques. So if you consider this random variable here, you can write explicitly its moment generating function, basically because, so the main thing is that Gaussian random variables are nice in the sense that if you take an orthogonal matrix and you multiply it by a Gaussian random vector, you still obtain a Gaussian random vector. So yeah, using this one plus properties of the chi-square distribution and Chernoff bounds, you get this result. And then with the trick of the previous slide, you get automatically this this tail bound for the Hutchinson trace estimator with Gaussian vectors, in which basically to obtain accuracy epsilon with failure probability delta, you need this number of samples, which still has this 1 over epsilon square thing, the logarithm of 2 over delta here, and then it has the squared Frobenius norm of A. So for Rademacher vectors, the analysis is complicated by the fact that if you take an orthogonal matrix and you multiply it by a Rademacher random vector, you don't obtain a Rademacher random vector. But let's say the nicer thing for Rademacher vectors is that they're bounded. So the first thing one can try is to exploit this boundedness and get bounds of this form using Hoeffding's inequality or Bernstein inequalities, which are concentration inequalities that hold for sums or means of independent random variables which are bounded, and in the case of Bernstein inequality, that have bounded variance. So what you get with these results is these two lines here. So this is what you get with Höfting, and this is what you get with Bernstein. And unfortunately, in both cases, you get an explicit dependence on the size of the matrix. So, so this is something we want to avoid. So this is, so I've been like presenting a couple of estimates, so I just wanted to show you a plot. So here I'm considering two matrices. So the matrix on the left is basically a random matrix, and it's just basically has no it's full rank, no eigenvalue decay, more or less. And the matrix on the right has some algebraic eigenvalue decay, just to take two different matrices. And here so on the x-axis there's the number of samples, and on the y-axis there's basically the value of epsilon such that this holds. So I'm fixing the failure probability to be 0.1, and then so to compute this for the bounds, I just like work out by hand what epsilon is. And so this is corresponding to Höfting, Bernstein, and the estimate I showed you before. And these are these lines. And then this blue line is what happens in practice. So basically I compute, say, 100 of these estimates and throw away the worst 10% and then plot the error of the largest error of the remaining ones. So you see that these estimates are off by a factor about 2 here and about 3 or 4 there. So now here you clearly notice that the estimate from Bernstein inequality has a different slope from the other ones. So what happens is that, so this, I'll go back one slide. So this estimate has 2 terms. When epsilon goes to 0, which means also when capital N goes to infinity, the term that dominates is this one. But for epsilon and N sufficiently, so for epsilon sufficiently big and N sufficiently small, which is the case here, this second term dominates. So what happens in this picture is that if I go on and increase capital N a lot, then this yellow line will be asymptotically like the other 3 lines. But this doesn't look good because this matrix was 2000 by 2000, so it doesn't make any sense to consider more than 2000 samples, because with 2000 samples I could compute exactly each entry of the diagonal of the matrix and then and then obtain the trace exactly. So for this, for the analysis with Rademacher random vectors, one needs to do something to use tools which are a bit more powerful. And in particular, there's this Hanson-Wright inequality, which says, so this is a very general inequality, very general concentration result for quadratic forms of this form involving a random vector X with sub-Gaussian random variables which are independent. So I put here the definition of sub-Gaussian, but okay, let's just say Rademacher random variables are sub-Gaussian, so one could use this result. And this is somehow similar to the form of the result for the Gaussian case. The only problem, so it has this term with the square Frobenius norm of A. The problem is that we don't know this constant C. So, so there are several bounds for Rademacher random vectors which somehow make this constant explicit, and here I listed some of them. So actually what we managed to do was to improve them. So here the best one is this one, and we got a factor 8 and 8 here, basically by combining the arguments in this paper, in this work, which is actually a master thesis, and this book. So what we get, okay, so there's an assumption that is not problematic, let's say, we're assuming that A has 0 diagonal. And then basically, one can prove that the probability that the absolute value of X transpose X is larger than epsilon is bounded by this quantity here. And I mean, the proof goes via logarithmic Sobolev inequalities, entropy method, and Chernoff bounds, but I will not say anything more about that. But then again, so we have a bound for one quadratic form, and using the sort of embedding trick, we can get a bound for the Hutchinson trace estimator, which is this one. So to get this, we need a number of samples, which is proportional to 1 over epsilon squared, as we would expect, logarithm of 2 over delta. And now here we have the Frobenius norm squared of A minus the diagonal of A. Minus the matrix containing the diagonal of A. And this is how the bound looks like for the example before. So it's this green dotted line, which now sort of follows more closely the true value of epsilon, such that this is satisfied. Okay, so here I have another example. Here I'm trying to count triangles in a graph. So basically, if you let B be the adjacency matrix of an undirected graph, in which you put 1 if there's an edge and 0 otherwise, then the number of triangles, you can write it as 1/6 of the trace of the cube of B. But anyway, so I was just, this was just an example. So here I'm comparing, so here I fix a failure probability delta equals 0.05, and then I let the number of samples go from 1 to I don't know, 10 to the third, or yeah, something like that. And I compute the error from our estimate, like the epsilon that I will get from our estimate from the previous estimate, and this is what I obtain empirically. So this light blue area indicates the 95 best obtained error. So it's just it means like for 100 samples, the errors were in this interval here. So what we care about is the upper border of the shaded area, and we want that to be close to the estimate. And you see that, so on the left it's for Gaussian random vectors, on the right is for Rademacher random vectors, and so the estimate somehow it's tighter for Gaussian random vectors. For Rademacher random vectors, it's basically off by a factor 2. But okay. So something like a small digression I would like to mention. So these bounds for Rademacher vectors can actually also be used for symmetric positive definite matrices. So this is okay. So this is the best available result for symmetric positive definite matrices. So if A symmetric positive definite, you can get a relative error bound. Okay, this is not possible for indefinite matrices because for an indefinite matrix, it could be non-zero, but then its trace is 0. And even in that case, if you do the Hutchinson trace estimator, it doesn't tell you that the trace is 0. So you get like, you would divide by 0, you cannot do that. So, but this is a result for symmetric positive definite matrices. So to obtain accuracy epsilon, you can take capital N to be 6 over epsilon squared times the logarithm of 2 over delta. But basically, if you take the bound for indefinite matrices and you divide everything by the trace of A, which is different from 0 in the symmetric positive definite case, you get something which is similar but also has this factor mu, which is the spectral norm of A divided by the trace of A, which is smaller or equal than 1 and can be smaller by factor 1 over n. So this is what happens for an example. So here I took two matrices, two symmetric positive definite matrices, one with a very slow singular value decay, one with a faster singular value decay. And I'm plotting the epsilon corresponding to capital, like for each capital N number of samples, I'm plotting the estimated epsilon in practice and the estimated epsilon by the estimate of the previous slide, and in black the estimate, like the general estimate. And I mean, you can get a better estimate, not always, but yeah, somehow the estimate of the previous slide is adapted to the metric. So if you have a faster singular value decay or a slower singular value decay, it follows the actual behavior of the estimator. So this is a summary of the first part. So what I presented were tail bounds for the Hutchison trace estimator, which is this one. And well, let's focusing on indefinite matrices. This is the number of samples we need for Rademacher vectors, and this is the number of samples we need for Gaussian vectors. So note that the differences are, okay, a factor 4 and a factor 8, whatever. And then here that you don't have, so the diagonal of A does, nope. The diagonal of A doesn't influence the estimate for Rademacher vectors, while it does it for Gaussian vectors. Okay, I'll make a pause. Are there any questions at this point? Right. Okay. Okay, then I'll go on. Recall that we were interested in computing the determinant of a matrix. So via this formula here, so that the log determinant of B is the trace of the logarithm of B. So we want to compute these quadratic forms where A is the logarithm of B. So we need a way to compute this xi transpose times the logarithm of B times xi. So now I'm going to tell you how you can compute these quadratic forms. And basically there's a nice connection between quadrature rules and Krylov subspace method, in particular the Lange-Soch algorithm, which I will try to briefly explain now. So if you, okay, let B be your symmetric positive definite matrix. You take a spectral decomposition, Q times the diagonal matrix containing the eigenvalues times Q transpose, and a vector X in Rn. Then you can write X transpose times the logarithm of B times X as an integral of the logarithm of the logarithm on the spectral interval of B with respect to a suitable measure. Now this measure is defined here. It's discrete, it's concentrated in the eigenvalues of B, and the weights are well basically defined by the eigenvectors of B. So now if you have an integral, what you can do is a Gauss quadrature and approximate it with a sum of, so you will have some nodes and some nodes theta I, some nodes wi, and you will have m of them. Assume that m is much smaller than the dimension of the matrix, and you just approximate the integral in this way. So the thing is to compute the weights and nodes of this Gauss quadrature rule, you can actually use Lange-Soch algorithm, which was presented before, so I don't need to say anything about this. But basically, what you get is a 3-diagonal matrix, symmetric matrix, which we call Tm. And what happens is that the nodes, so if you consider the Gauss quadrature rule with m points for the integral of the previous slide, the nodes theta I are the eigenvalues of Tm, and the weights Wi are the squares of the first elements of the normalized eigenvectors of Tm. So at the end, doing Gauss quadrature for computing X transpose logarithm of Bx boils down to applying m steps of Lanczos algorithm to the matrix P with starting vector X, then taking the matrix logarithm of this small three-diagonal matrix, and then taking the entry in position 1, 1. So the thing is that to bound the error of such approximation, you can rely on polynomial approximation results. So the general idea is that Gauss quadrature is exact for polynomials up to degree 2n minus 1. So if you know a good polynomial that approximates your function, then you can obtain a bound for this quantity X transpose f of a times X minus the approximation of the integral. And if your function is analytic in a suitable region of the complex plane, then you can use Chebyshev polynomials and bound the coefficients of the Chebyshev polynomials basically by something. Basically, you can prove that if your matrix has eigenvalues in minus 1, 1, and your function is analytic on an ellipse, which like this, which has the Fauci in minus 1 and 1, and has the sum of the semi-axis equal to rho for some rho larger than 1, then the Chebyshev polynomials, the coefficients of the Chebyshev polynomials decay with rate rho to the j, with rate rho. So what you get at the end is that this approximation of the quadratic form converges with twice that rate. Okay, so what happens with the logarithm? So for the log determinant, we're just interested in f equal logarithm. And what happens is that, I mean, the problem is that the logarithm has a singularity in 0. So what you need to do is to rescale and shift this ellipse in such a way that the lambda, in such a way that it covers the interval lambda min, lambda max, and it doesn't cross 0. So basically, this is and then you take the largest ellipse, like the largest ellipse you can afford, and the elliptical radius is related to the condition number of the matrix B. So yeah, you can take something like this. And what you get is a convergence result for X transpose logarithm of B times X by this approximation. So basically this error. So this is what we want to compute, and this is what we get via Lanczos. So this is the entry in position 1, 1 of the logarithm of the three-diagonal matrix, just rescaled by the square norm of the vector. And here you get something which is more or less constant, and then this term to the 2m. So this is the convergence rate. So this quantity converges exponentially. Okay, so now that we have this, we can combine, we can put everything together. So basically what we wanted to compute was the trace of the logarithm of B, but we cannot do that. So we want to compute the Hutchinson trace estimator of that, which is 1 over capital N times the sum of quadratic forms of this kind. But still, we cannot do that. So what we actually compute is this approximation here, in which each quadratic form, for approximating each quadratic form, we compute the three-diagonal matrix Tm, its logarithm, the entry in position 1, 1, and then we multiply by the square norm of the vector xi, and we average. So combining the analysis for the Hutchinson trace estimator and the analysis for the Lanczos, for the quadratic forms, you can get a bound on the number of samples and the number of iterations that you need to ensure that the probability that this approximation differs from the log determinant of B by more than epsilon is smaller than delta. And basically what you obtain, so this is for Rademacher random vectors, basically what you obtain is that the number of Lanczos iterations needs to be proportional to the square root of the condition number of B. And the number of samples needs to be proportional to epsilon to -2, log of 2 over delta, and then this term depending on the Frobenius norm of the logarithm of B. Okay, there's a similar result for, you can do the same thing for Gaussian random vectors. The only, let's say, annoying thing is that they're not bounded, so you have to, so we have like an additional technical assumption that allows us to have the norm that basically says that the norm squared norm of x doesn't go out of control. But yeah, here it's basically the same thing. The number of Lanczos iterations needs to be proportional to the square root of k, and the number of samples is proportional to epsilon to the -2 Frobenius norm squared of the logarithm of B times the logarithm of 4 over delta. Okay, so here are just a couple of examples in which, so like illustrating the bounds of the two previous theorems. So here I took, so the matrices are rather small because so that I could compute everything exactly. So this matrix is a symmetric positive definite matrix coming from a discretization of a 2D Gaussian kernel. And here in plotting on the left, the relative accuracy of the Hutchinson trace estimator versus the number of samples n, where for the Hutchinson trace estimator, I approximated the quadratic forms using Lanczos algorithm. And on the right, I'm just plotting the Lanczos part of the algorithm. So here, like the more wiggly lines are what happens in practice, and the straight lines are what's estimated by the previous results. And you notice okay, so this is one. This is another example. This is a sparse matrix, like bigger matrix, but sparse. And you notice that, so for example, this purple line is for Rademacher random vectors, and this red line is for Gaussian vectors. And you notice that for Rademacher random vectors, the accuracy is much better. And this is due to the fact that this matrix B, and also the previous one a bit, has large elements on the diagonal. So Rademacher vectors are better at detecting, I mean, they detect the diagonal exactly. So it's only the off diagonal part that gives you an error. So that's why they're different by an order of magnitude, basically. Okay. This brings me to the end of the talk. So just to summarize, so in several applications, one wants to compute the trace of something, especially matrix function. For example, when computing the determinant of a matrix. You can get approximations of V transpose f of B V via quadrature, which is equivalent to Lanczos. So, okay, I mean, this still depends on the condition number of B. So yeah, cheap with some caveats. And then for estimating the trace, you can use this Hutchinson trace estimator, which I recall here, which you can use for any matrix which is available through maybe approximate matrix vector multiplications or quadratic forms. Okay, yeah, that's it. Thank you very much for your attention. Okay, so you're using random vectors with Gaussian statistics to sample your matrix to compute trace. You get 1 over square root of n convergence. This reminds me of Monte Carlo integration. Is there a way to use quasi-random sequences to create quasi-random vectors, which will give your algorithm better convergence behavior? Okay. So I don't know exactly about quasi-random sequences, but so some people tried to use multi-level Monte Carlo. Yeah, multi-level Monte Carlo to speed up the convergence of this estimator, and in practice it works. So, okay, they did it while approximating these quadratic forms with polynomial interpolation. So it's something a bit different from this setting, but still related, and it worked a bit. Like they had some improvement. So this was Holman and someone else, which I can't remember. So there's actually other things that you can do to speed up. So you can do other algorithms which are not Monte Carlo for doing faster trace estimation. For example, for symmetric positive definite matrix, there's a recent paper. They introduce an algorithm called Hutch++, in which basically they combine randomized trace estimation. So this Hutchinson trace estimator with the randomized singular value decomposition. And they prove that for symmetric positive definite matrices, you get faster convergence. I hope that more or less answers the question. But are there other? Yeah.
Yeah, so the bound that you showed for number of Lenshof iterations looks quite large.
Yeah.
I guess it's just a bound because I was thinking about looking at a matrix that had all eigenvalues equal to 1 and then 1 10 to the minus. I mean, the condition number would be quite large, but I would guess there's quite a few iterations in that case.
Yes. So one case in which, so this is one case, for example, in which that bound is just horrible. Is if your matrix is more or less low rank, it's numerically low rank, then you just converge in a few iterations, and that's okay. Yeah, and also that case, I think it's linked to how well the eigenvalue, like the Krylov subspace, approximates the eigenvalues of A. So if somehow after a few iterations you have a good approximation of everything, then it converges much faster. Yeah. So in general, it's an it can be a big overestimate of the number of samples you need. But in some cases you really see this that this condition number grows.
It can be tight in some cases.
It can be tight, yeah. I mean, I don't know how tight, but for sure you see that if you have a bad condition number, this thing is not really converging nicely, which is a problem then.
I have a question to follow the question in the chat box. So I think the quasi-random vectors, I think in my opinion, it's we can control the seeds to generate the random numbers.
Yeah.
So I think there are so many techniques in variance reduction, such as importance sampling or like common random numbers. So I think if you control the seeds in generating random numbers, maybe you can convert better. I think. Have you tried that? Because if you use importance sampling or common random numbers, I think you can reduce the variance in your estimated expectation. the estimated expectation, right?
Okay, so I didn't
So
try
so
that.
so I'm just curious about if we use this variance reduction techniques, can we improve the convergence?
Okay, so I'm not really familiar with this seeded random numbers. Is that okay? I don't know. I don't know what happens actually.
Hi, this is the original questioner. I'm Stuart. Yeah, I guess that was my question, is that it really is a matter of sampling. And the problem with purely random sampling is that the sample points that you get are sort of clumped and have bad statistics compared to some sampling method that can sample your space more uniformly. And that's what the quasi-random sequences give you. And they're used a lot in high dimensional integration, but I know nothing about how they would be used here. I was just more curious about whether others had thought about
it. Sorry, I didn't really understand the question.
I think it's just more comments, Alice. We could get one more question we have from here.
So Alice, thank you very much for a nice talk. And actually, I wanted to follow what Jim said. I haven't, because in those bounds, you always have a probability, right? I mean, so if you want your bound to be satisfied with a high probability, then probably those number of Lanczos iterations will be much higher, because you kind of force it to make it such that with high probability bound is achieved. So I think that may come into game also. But the question I wanted to ask you is, so a lot of these results on randomized, the theoretical side is based on the random matrix theory. And of course, you use the results for the Gaussian, and the result by Avron is also for Rademacher. But how does it look in terms of different distributions? So there are, like, in randomized numerical linear algebra, there have been people looking on different other different distributions, and the problem is we are lacking results in random matrix theory. So I'm wondering if you or anyone else in the audience may have some tips, since you probably read a lot of these things during your thesis, if you came across some more detailed or maybe more insightful results.
Okay, so I'll reply first to the first comment. So the number of Lanczos iterations doesn't really depend on the failure probability. At least, so for the Rademacher case, it doesn't depend. And for the Gaussian case, I mean, yes, still it doesn't really depend. Okay, so the only thing that depends on the probability is the fact that if you want a better failure probability, you need more samples, so you need to compute more quadratic forms. But then the bounds for each quadratic form is just the same as before. And for the second question, so I focused really on Gaussian and Rademacher, but in general, what I would say is if you have, so you can get bounds for the Hutchinson trace estimator from this inequality here. So if you know that for a certain kind of nice random variable, you have a constant, you know what this constant C is, then you can automatically get a bound for the Hutchinson trace estimator. But yeah, I'm not aware of like other specific.
I think there are.
No.
Yeah, we have time.
Yeah, just a comment. All of these methods do not exploit structure, right? You don't either.
Right.
A is just something, but in some situations, you know that A is nearly sparse, and then you can do something, of course, that's much more powerful than all of this. But any work that's been done recently that tries to essentially exploit structure in some ways? I mean, apart from sparsity, perhaps is the simplest example.
Perhaps.
Any recent work that tries to exploit sparsity? Not sparsity, but structure in general.
Yes, so there's work that tries to exploit sparsity. sort of like approximate bandedness, not my work, but basically the idea is that if you have a matrix which is more or less banded, so maybe not, so let's say here you see that Rademacher random vectors are good if the matrix is more or less diagonal. But if it's more or less, say, tridiagonal, you can use vectors which are called probing vectors, which are like 1, 0, 0, 1, 0, 0, 1, 0, 0, and so on, and then 0, 1, 0, 0, 1, 0, 0, and so on, and then 0, 0, 1, 0, 0, 1, and so on. And you use these vectors to compute the quadratic forms. And I mean, if you have a nice off-diagonal decay of your matrix or matrix function, then these work, I mean, have exponential convergence and whatever.
This has been done some time, but there's nothing else that's recent.
I don't think so.